Ey, entonces nadie va a entrar a Zoom. En YouTube vamos a hacer todo.
Aquí es en Meeting, pues. Es aquí en Meeting.
Ah, es que aquel, no, es que aquel había puesto el enlace ahí, pues ah,
Ahí están pidiendo permiso. Puros nombres indios. Visay, ese nombre es indio.
ahí darle que sí para habilitar los comentarios. En OBS. Date a OBS, compartir pantalla ahí.
Ahí dejar, ignorarlo. Ignorarlo.
No, pero ¿qué le dice iniciar? A la madre, los vas a trolear. No, o sea, bueno, si no le he dado a iniciar, no hay ningún problema. Ah, pues sí, ya estás en live. Ni modo.
Dale, ya.
Pero ya, es que, vaya, ahí andate stream y ahí está. No, pero ahorita no estás en directo. Pero es que, creo ver. Es que a mí en YouTube no me ha salido nada. Ah, sí, sí, sí. Sí, estás en directo. Dale, cerralo. Cerralo, no importa. Ajá, ya no. No, ya no. Sí, lo hizo solo. Lo hiciste de otra forma, pero está buena. Ah, pero sí, ya ofreces. Ajá, ya no. No, ya no.
Quiero ver si me sirve la pizarrita, fíjate. El Jamboard. Porque el Jamboard puede usarse desde. Tengo usado Jamboard, la pizarra de Google. Yo,
Mejor,
yo la uso desde el celular, uso el Note. O sea, tengo el Note, tengo el lapicito y dibujo así. Porque con el mouse está
fíjate
feo.
que mejor detenerla en vivo, porque no tenés configurado así como toda la pantalla extendida. Hay un pedazo negro. La resolución que estás enviándolo a 720p. No hay que cortarla en vivo mejor.
Hello. Okay, cool. Where you guys from? I'll save it. Can you write it down?
It's Central America. It's a country from Central America. It's
Wow.
almost 1 hour overlap from the United States.
I'm from India.
Hola, buen día.
Hello, which language will this be in?
It would be in English.
deep learners. I'm Andrew Ng, founder of deeplearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the deeplearning.ai offices and meet some of the teams so that you can see where it all happens.
Oh, hi, Andrew.
Do you want to tell our friends at Pie&AI what you do at deeplearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There is never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so I'll let you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pie&AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
That's really important work. Well, it's nice chatting. And now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pie&AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, Hotel.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pie&AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot, both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
I will share my screen. Well, good morning, everyone. We're going to talk about self-driving cars and the foundations. So we're going to talk about some concepts related to the perceptron, basically the same ideas about neural networks. And the main challenge that it's behind self-driving cars, that it's convolutional neural networks. We're going to have some introduction, maybe a theoretical introduction. Then we're going to make a workshop, a live coding, some live coding, a small, how we can apply all the knowledge in an NVIDIA model that it's maybe in production. And so we're going to see some interesting facts. So happy to share with the community, and we're going to start. So basically, when we talk about machine learning, um, we talk about data, we make predictions, and we're going to make decisions. That's the concept from a raw input. Then we call something in machine learning that is called feature engineering. It transforms some characteristics to make a real-time prediction. And then we're going to make a decision based on a model. It can be supervised learning. We talk about tabular data, unsupervised learning. Maybe we work with text. We have natural language processing, or maybe with robotics we have some things about reinforcement learning. So maybe it's like a good thing to know that how we're going to transform data, and data is the power of artificial intelligence. So we're going to talk about that. So um, I like that diagram because it's like how you can summarize how artificial intelligence work in the real world. We have human judgment, where it's basically a behavior of what something can happen based on data. Maybe in that point, we talk about use data and make some sample statistics. It's not about machine learning. Then we have rule-based systems, as we'll start to talk about supervised learning, and then we go to the unsupervised learning and to the deep learning, which is the field when we talk about neural networks. So basically, in all the fields of artificial intelligence, we have like a sample from data collection to the final the step of building a machine learning model or a deep learning model. So that's an introduction. We're going to talk about this concept. Basically, it's called the perceptron, but it's interesting to understand in how a deep learning model work. Well, we have raw inputs x1, x2, x3, x4, x5. It's a vector. Then we have weights, which is w, and then we have this zeta equals x times w. That's maybe the weight, and then we have an output. That's the main concept of a perceptron. So some interesting facts that we have to remember is this. I will use a Jasper here. I think that we can use it here. I think that W maybe here. We have to understand some things. I think that when we have like here in the board, I will show you. It's interesting that understand that, for example, here you have like in R3, maybe if you are familiar with some math, we have a plan. We have zeta, x, y, and zeta. That's in R3. So maybe that's interesting to remember because something we're going to work in R2. So that's like a challenge that we're going to face. So then we're going to talk about so basically the main intuition behind neural networks is work with a round input x, then we use a weight, and to the final prediction we have to understand some bias that maybe a neural network has. So maybe it's an equation, and then we have raw vectors and raw combinations there. That's interesting to remember. So, for example, if we have a dog and a car, we have an input. Basically, neural networks didn't understand like how it's a dog. They transform in a vector, which is a process called one-hot encoding. Maybe dog will be a vector 0, 1, 0, and then we have an input, and then we have to pass from the layers to have a final output. That's important to remember in how a neural network works. So basically, there are two important things about neural networks. One is an activation function, and then the transform of the raw inputs x1 to xn, and then transform that input. So I think that it's clear here. We have like some input x0, x1, x2, xn. So basically, I think that when we use and we try to understand, for example, an activation function that is a segment function, the main important thing is how we can reduce linearity or nonlinearity in the neural network. So we're going to talk about some a raw vector with the inputs. We multiply that for the weights, and then that's the main challenge when we're going to talk about neural networks. So basically, in that definition, one of the main solutions or challenges is select an activation function that will be working. Here, what you can see, it's a matrix, it's a transform matrix. So basically, it's how it can work. If it's a matrix, it's 1, 2, 3. So we change rows and columns between order, and that's a transforming matrix. So that's challenging. So I think that one of the things that we have to work with machine learning, it's the bias. That is basically a term when we use to produce like results that maybe are not accurate with the assumption that we make during the training. So that is it's we have to consider when we're going to talk about neural networks. So there are many activation functions that are working to apply machine learning to real world problems. So if we see, for example, we have the sigmoid function that it's really common, basically to reduce some linearity, the ReLU function, and in the case of self-driving cars, we use a lot LU because we're talking about work with neural networks when the raw inputs are images. So that's how maybe we can activate all the neural networks during the time. So that's how we can work. So basically, that's like a trick of how you can remember the form. If you see like the picture, you can remember the form, and or maybe the definition of the main activation function that we use to work with neural networks. So basically, a neural network it's a combination of linear and nonlinear transformation. So we have right now here you have an X vector, and you have a transformation. Basically, that's the first layer. And what we're going to do, we're transforming raw vectors in good features. So basically, W it's a weight, and we have a layer. So basically, here we have a transformation from the matrix and the bias. So basically, the main selection between the transformation, it's how the memory of the neural network is learning. So that it's two process. The third one is forward propagation. It's how the when the neural network start to work from here, from the beginning. I think it will be left to right, and the back propagation too. And that's the main challenge of the loss function. That it's how the neural network maybe lost accuracy during the training. So that's the main concept. So basically here it's important to remember what activation function we're going to use, because this is the main challenge when we train deep neural networks. So basically, one of the things important in neural networks is how we can reduce linearity. That's how we can predict a good equation and with the accurate prediction. So maybe if you see an x here, that's a raw vector with the prediction. Then we have a weight and we have a bias. So basically, how we can reduce linearity is basically with the weight. So that's a good approximation of how it works. So basically, if, for example, here you have one thing that happened with neural networks, and then there is an example with PyTorch. It's that when we're going to do like a classification task, we have a decision surface. So maybe if we have alcohol and proline, we're making a classification between wine. In classic machine learning, we can use some algorithms to classify the data. But here, the thing is, it starts to being more complex, the decision surface, and to make accurate decisions. So I think one of the main challenges is understand what, for example, in the model, if we use PyTorch here, uh, how we can use and select the activation function. One real word trick is understand, for example, how it's we're testing, we're like making an experimentation. So you just start like see if the model is maybe doing an overfitting and how it works with for example, if you have 90% of accuracy, you maybe start to think about overfitting. So we have to adjust the activation function. And for example, when we train images, one of the main challenges to reduce overfitting is maybe do a process called data augmentation. And then it's a pre-processing when you adapt the raw vectors that are in the pixel from a convolutional neural network, and then go through all the surface. That's a main approach. I think that one of the main challenges that we have in real world is overfitting. And I think that one of the mistakes, or basically the challenges, is when we use too much parameters, we start to make like overfitting. And so one of the selections that we have to use to train that, it's select an accurate activation function and maybe the architecture. Maybe if, for example, if we're training like a time series data, we have two selections. Maybe we would use a large, long-term memory deep neural network. That's like a special trick of recurrent neural networks. Or maybe you can start to use another architecture. Maybe when you have a lot of parameters, you can start only not to use deep learning. Maybe in time series forecasting, you can use like gradient boosting techniques to maybe train that. So that's the main approach. So right now, that's like a real introduction of how neural networks work, like in a theoretical way. So basically, we have like two main fields of deep learning that we're talking about. One is computer vision, uh, and there are a familiar of models. Maybe there are a lot of convolutional neural networks, and maybe some trained models such as ResNet, ConvNet, and right now that are so popular with Hugging Face, some transformer architectures. And one of the main challenges is to identify images and to predict that classification task. And then another field that it's important is natural language processing. Basically, it's how we can process raw data, and maybe there are some real world tasks such as sentimental analysis, text classification, text summarization, that are accurate to work with the data. So that's like how an approach. I think for training neural networks, I I I think that there are some steps that we can follow. One is prepare the data. In the preparation of the data, there are a lot of pre-processing that we're going to see in the real world example. There are some normalization of the variables. Normally, we have to adapt a median, and there are the T processes that one hot encoding. What is one hot encoding? It's a process when you have like, I will show you here. Here you have, you're predicting in the neural networks if it is a dog or a cat. So one hot encoding is to transform the raw pixel, for example, is 24 times 24, and to put like 0, 1, 0, it's a vector with the words of dog. So that's the one hot encoding that it's interesting to remember when we talk about neural networks, especially convolutional, that it's a part of computer vision. Then divide the data, that's train and test it and validation, that's important. Then select the architecture and the loss function. There are many loss functions that we can use uh, to make accurate predictions. And then select parameters, that's important, like the throughput rate and how it can work throughout the time. That's a challenge. So then, for example, we can select the number of epoch. What is an epoch? It's like how many times it starts from here you can see it. An epoch, it can be one iteration from dog to dog and cat. You have two images. So then you have like an epoch. When we have a complete training, that's a forward propagation and there is a back propagation. So how many epochs the model will be trained, that's an important thing that we have to understand in order to make like accurate convolutional neural networks. And maybe repeat the steps, that's important. So that's the main thing. So we're going to pass to the main core, that it's understand convolutional neural networks, because self-driving cars are made and trained by the end with the sensor fusion data and working with a convolutional neural network. So if you see an image here, that's a cat, it has 32 times 32 pixels. So what can be the main challenge to train? Well, we have to pass the parameters that are here to all the deep neural networks. So we have a flattened like a step here, and we have like some learned weights, and we have an output class. So maybe there is an important concept that we have to talk about here, that it's the convolutional filters that are interesting to train a neural network. For example, here, if you see like a dot product here, we have to select like a patch of or a filter from the raw image, and then pass that to the flattened layer. That's an intermediate layer with, like if you imagine a human brain, like how John LeCun create that, how you can remember an image. So that's the first memory, it's a flattened layer. Then you have a dot product of the filter. That's a filter, 5 times 5 filter. And then you have a complete output. Um, that's an approach of how we start to think about that concept. Um, then I think that it's important to remember how the main parameters that we have in neural networks. I think that one is the input vector. Here is 32 times 32. We have the filter size. It's right now it's a filter of the convolutional neural network. It's 5 times 5. That's pixels from images. Then we have an output. The output is the dot product between 32 times 25. That's the dimension. So basically, the dot product, a simple operation in algebra, can give you the output. So that's like how we can subsample layers in all the steps. So I think that it's important if you have like we have like a convolutional filter and how it works. So basically, we have a kernel. Basically, in the image, the kernel can be that. So that's a 3x3 kernel. Imagine that the image maybe has uh, 25, 26 times 26 pixels. So one of the main challenges here is how we can make like a convolutional, or maybe how we can test the size of the kernel. So basically, here we have some weights. Here in the matrix, that's a weight matrix. Um, so maybe it's like we're not going to code that basically in the framework, but it's interesting to understand that for each like a block of pixels that we have here in the left, 3 times 3, we multiply each pixel by the corresponding entry of the kernel. The entry of the kernel here is the entry of the filter. That's the main measure of the weights. So basically, we have to make like a pooling layer here to understand how it can be working throughout the time. So basically, we extract a little bit of the image, and imagine if you're training like linear regression model. That's like a comparison. So maybe you test, or you take like 3 rows and you have like 20 rows. So that's how you can start to test the size of the kernel and how the convolutional filters work in real time. So in some cases, we don't have only one images. The case that we have here is when we have one image. The process is we take a filter, and then we pass to the flatten layer, and then we make it to the dot product to have an output. And for example, here we're classifying if it is a dog or not. That's an image classification task. So, but in real work, we have like multiple channels because we have a lot of images. So maybe the transformation, it can be the same. We throw the image has 32 uh, times 32 pixels. So we multiply that for the channels. There are 3 channels in that example, but it can be a millions channels. That is the images that we're making the classification task. So we have the same working thing. We have a forward propagation when we start that the deep neural network main and how it works, and we have a back propagation. Then it may be we have to understand that the neural network lost information. So the most accurate prediction is when the raw image in the flattened layer remember all the information. That can be an accuracy of one. Maybe it's the accuracy between 0 to 1. So that's not happening in real world. Maybe when we have like that, we have an overfitting process because raw images maybe have some different pixels, colors, and variations. So that's how it works. Then we have to make like everything the dot product, and we have the output class. Um, Another important concept that we have to learn in convolutional neural networks, it's how filters work. So we have a concept called strides that it's used in convolutional 2D and convolutional 3D. How it works? Well, we have here an image. The first step that we talk about is take from the whole process an important or a small step. It's a filter 3 times 3. So maybe when we talk about the stripe, it's we're talking about making a raw transformation of how many steps we're going to take to go from the first class to the last class. So that's an stripe. Basically, you can understand the stripe of how it can be using during all the training steps. So another important thing that we have in 3D here, it's we have the padding. I think that it's like we have the same padding in all the images. So if we're going to extract a raw like pixels 5 times 5, and then we have to uh, use the same padding in the image filter. So we have the straight, and one important thing is that how we can select the filter. So the pairing process, select the filter and stride it. The stride is like passing that filter to the first flattened layer. So that's important. So in deep neural networks, we're working in fully connected layers. So when we talk about a raw vector, here imagine you have a dog classification in convolutional neural network. One of the main challenges here is that how the main function is going to work to make the classification task in forward propagation or in back propagation. So here you have like x, it's a raw vector. Then you have a function. What is that function? Is the activation function. So maybe we can just stand here in the example, we can use relu, elu, and we're going to pass all the information from that raw vector to the first flattened layer, and that's how a neural network starts to learn over the time. So maybe the main challenge is how in that F we adjust the weights, that it's the weights of the deep neural network to make an accurate prediction. So it's important to understand how we can reduce linearity during the training and how it can be working all over the time. So maybe it's important that when we train, we have to be like accurate how we can make the pre-processing, because uh, if we also train models in supervised learning, the most important thing is good features. And basically, if we are training, imagine like a credit scoring machine learning model. We have age, we have some people and some raw characteristics. So basically, before we train a model, the good data is good artificial intelligence. So the main steps in the processing are really important. Here, it's in convolutional neural network, the data augmentation process is one of the main importance. And so maybe it can be challenging to adapt and to like preprocessing the images and maybe fix filters to have accurate predictions. So we're going to talk at the end about self-driving cars and how it works in real time, in real world. Um, we have like some fatalities of how maybe uh, in real world some completely autonomous have like accidents. Uber, and then it's a Tesla autopilot. Maybe it's like we're challenging the neural network to learn about, for example, the steering, maybe the access of how it works. So that's a real challenge. So, for example, here some people, Elon Musk says, my guess is that probably in 10 years will be very useful for cars to be built that are not fully autonomous. Um, Rodney Brooks, like it's an investor, said that a majority bans manually driving cars from a non-trivial portion of a city. I think that in the United States right now, yesterday I see a paper from NVIDIA. I think that less than 40% of the main car accidents that were doing by, for example, people that is in no conditions to drive are reduced using autonomous vehicles. So that's a challenging thing, and also that it can be useful for supply chain things. So I think that one of the most important things that we have to remember when we talk about self-driving cars is when we always need the human in the equation. As Martin Short said, that is the director of Nissan. They have like some projects related to autonomous car, but they are maybe not in production. They are maybe in the labs. So that's how it can be a challenging. Basically, for example, in some countries that is not good the location, we have like a teledetection and maybe how we can adjust all the sensor fusion technology there. So that's think. I think that here we're going to talk about a real world. Uh, we have that data set from Mountain View driving data from 10 years. So we're going to start to train. So let me show you my screen with the code, and we're going to start with the workshop. So we're going to use like a collab. So I will share with you the link here, and we have a repo too. So you can start to see in real time how it can work. So here we're going to see here. I will share with you the GitHub repo that we have of Pie&AI in Salvador. And you can see all the most of the details that we're going to use today. So we're going to start here. Maybe we're not going to code everything from scratch because we don't have time, because it's like a lot of images. So we're going to be telling everything about how it works. So I will share my screen. I think that it's, well, I think that I need an accelerator here. Well, here we're going to use the data. I will show you the repo and how it works. Here we have like a huge data set of images that I may be images from drivers in Mountain View. Like there is a reduced way of how it works. So we're going to go through all the steps. So here we were going to use this paper that is an NVIDIA end-to-end learning for self-driving cars. So I think that one of the good challenges of we're practitioners of artificial intelligence is how we can read papers. So one thing it's good to know, and a paper maybe it's how the abstract is. So that in that end-to-end learning for self-driving cars, they use convolutional neural network. They use an architecture called ResNet that is good. It's a pre-trained model, a huge pre-trained model, and they use convolutional neural network. So one of the things that in that system is that they have that there are at the steering, and they have three type of camera: left camera, center camera, and right camera. That's connected to a NVIDIA drive. That's the computer that is there. So basically, we have data from a steering, angles, and without all the camera. So one of the viewpoints, it's how the system works, is that we have in the training model, we have left camera, center camera, right camera. We have data collected. So we have to make a data collection and data processing to train the convolutional neural network. One of the main challenges is, as we talk about propagation and the weight adjustment, is how it can be accurate to the convolutional network to use and predict in unseen data. So basically, it's not too simple to adjust that weight. So basically, how it can be worked, and the center camera of the car will send data to the convolutional neural network, and so the network will predict and to send to the NVIDIA that we have here, the NVIDIA drive, how it can be working in real life. So the first step that they do, it's like they start with a data collection. So data was collected uh, uh, by driving in a wide variety of roads, um, and basically in these cities, Illinois, Michigan, Pennsylvania, and New York. So they have like driving, basically how the driving parameters are. Um, what will be the architecture of the model? That is the data collection they have. It's a huge data set. Um, we have to make like data selection. It's like how we can select and sample the data. So right now I will explain you here the architecture of how it works. Let's start to here. We have input images. We have 200 gigabytes of data of images. So we start to train, and the first step is normalization of the data. It's mean 0 and the variance equal 1. And then we use data augmentation process, and we start to pass through all the layers here. And I think that one of the main challenges is to select the number of layers in the convolutional and how it can be the filters. For example, they make a lot of tests, and then they have a filter of 66 times 200. That's the first filter in the kernel. Then the another filter, and they start to make a convolutional feature map. That's a fully connected layer. What's a fully connected layer? I will show you here. It's the architecture. It's on a fully connected layer. Is here. They use like raw vectors, that's images. Here they make a real world transformation, and then they start to put here in the flattened layer the convolutional architecture. So it's a process. Then the main challenge basically is the weight adjustment between backpropagation, is how the information is worked. If we have an epoch, we go information from X to Y, and then it passing through all the layers. So the adjustment will be in the activation function that we talk here. The activation function here, it's like how it can reduce linearity from the transformation, so to make all the predictions. So and they work with data augmentation. Like it's our data augmentation. It's basically adding artificial shift and rotation, maybe change the filters, the size of the filters, and we have a good orientation. So they have like a simulation. They test it in real life, and we have like a simulation. So they have in real world road test, and basically the use of internal test. So basically, we're talking about a small part of self-driving cars, but basically the most important, because here the NVIDIA drive that the car have work with the accuracy that the model is going to test. So basically, the convolutional neural network is the best thing that in real life would adjust shift, rotation, speed, and how basically the car will respond to a brake. So how we're going to go to the code, and then here in the repo that we have here, we put that like if you want to test here, there are the images. Basically, there is the model. Basically, there is the notebook. So we use this data. It's like a log data, and we have to train like how the data is being collected about the parameters. So we're going to go to the code. I'm going to start using a feature, a TPU, because I need like a lot of training to work. So the first step, I clone the repo that is here in 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 the workshop. What I'm doing this, I'm cloning and I'm bringing all the images to the work. So um, here basically it's really slow because we went about talk about 200 gigabytes of images. Basically, I think that I will use here. Then I use a GPU. We'll try to connect here to the GPU. because we need it here to train that faster because it spends a lot of time. I will rerun that. Well, here we go with the code. Here we have the same imports. Here when we train a neural network, that's like we import some libraries to train. NumPy matplotlib image. It's how we can plot images with that library. Plotlib's good approximation, and then we have optimizers to work here. So we have like we're going to train that with TensorFlow because it's less expensive in computation. If we're training with PyTorch, it's like a little bit tricky. So I think that it's not charged here, the repo. Here in the repo, I will see how it works. It's not charged the repo here in the TPU. Give me a second. So basically, here I will see here in the images. So basically, one of the main challenges here, I think that I will use here. I will just here I will use that notebook because right now I don't have the instance of the GPU to train that because it can be kind of difficult to train that. So I will start here to use basically I'm depending on how they work. Or here is cloning the repo because I have an instance working here. So here I think that it works. Here is working I'm going to use an NVIDIA TPU with Tesla specification. There are maybe the processing, and we're going to use 3.6 gigabytes of RAM. So we have the imports here. One of the main imports is Adam, and then we import convolutional 2D, max pooling 2D, the output as the input of the hyperparameter and the dense. So CB2 is like computer vision stack to classify images, and we use some scikit-learn to basically divide the data. So here we have that. We have a center in the images of how it can be. Imagine if there is a driver, so there is some data here. Here you have a center, the data from the center camera, from the left camera, from the right camera. And then you have a measurement of steering. That's the angle of how it can work in the like in the process, and how what was the speed that is happening. What is important that because the neural network needs to adapt the steering, basically the speed and how it breaks. So that's an important thing here. So basically, we're going to see like how the data is. We don't have null values here in the logs. Here we want to make like a correlation here. It's like how it's and they are between the variables. There are no correlation there. If you see here, there is no like correlation between the steering or maybe the reverse of the throttling. So we're going to start here. Here in the data, we're going to plot the angles of the steering. I think that it's important to see here. And another thing that it's important here, it's like that I will plot here in 3D. I think that it would be here better. X I will put here. I will draw here the truthful. It's important that we can see it in the and then we can see here I will draw here the steering to see it in 3D. Then we have serum equals. Here I will see here. Here. But I'm going to just plot the data. That's images. That I will put here the speed. And I will see the reverse here. But what we can see here in 3D is that the main correlation between the speed that a car has, for example, it can change of the angle of the steering and how it works in the real use case. Here, like if you know, like there is like an explanation of how the convolutional neural network can adapt the parameters in the way that the speed increases or decreases. How is that? Um, we're adjusting the shift and the rotation of the and maybe the recorded steering wheel angle, and we are like shift and adapt that to how it can be in all the process of the convolutional neural network there. So basically, here we see another parameters there. So that's like how it works. So I think that we have like that images, and we have to process the data because normally the data from sensor it's not clean. For example, here we have the data and we have to remove paths here. There is a function in Python when we remove paths. So we define the functions here and we split, like it's a function. When you split data in Python, it can be used with re or regets function to split the data. So we apply that. We want to remove the I think that the path that the raw data has. So we have here, and we have here only the image. Here is an image of the center camera, the left camera, the right camera, the steering, the throttle, the reverse, and the speed. That is the speed in that time. How many? We have like 2 million images. So basically, it's important to clean the data. That's a pre-processing simple step. So one of the next steps here is basically we're going to visualize the data. So we need to see the steering, or basically the distribution of the steering wheel angle values. So we're going to plot that in the number of pins here. That is an histogram. We're going to use matplotlib here, and then we're going to like center in the list from -1 to 1. That's a distribution of how it can be the centers of the beam in the steering. So imagine we have here in the car, we have like a distribution from -1 to 1. So that's how it works. So that's we want to use another function. We have to remove index from the steering data. If you see here, there are some index in the data. If we see that data, have some index there. So we have to remove that index. So then the first thing is here we define a list. We start to iterate to the number of bins. The number of bins here were defined as 25 of how it can be done. So there is a first for, then it's a second for of the to go to the length of the steering. And basically, if here it's the steering angle needs to be more than the bins. That's why, because we need to accurate that the steering angle can be from -1 to 1 in the angle. So and then we append the list. Append is like we have one list and we append the data from the second list. That's a method in Python. And then we're going to remove the extra data that we're not going to use. Here it's just a remove function drop it's a drop function here when we start to do that. Here is we have some the total data, and we remove these samples. Why we remove these samples? Because they not they the main parameter where the steering angle have to be more than the pins. So that's how it works. Then we have an image here from the data directory. Here we're going to load the images from the image path director. So basically, I'm running a function to get the images and the steering data. And as we talk, we transform, and we need to transform the raw data that we have um, into into vectors. So we define a list from image path and from the steering data. Then we define a for um, from 0 to the length of the data. Then we select ilog is to select from the final index, and then we start to uh, load the data. What data we're loading? These images that is in the repo that you have. So, but we need to the first information. It's like we have to index the data and then to put it there. So uh, then we have to split the data. Here is like we are doing data. So basically, we define with scikit-learn. Basically, we define the test site 0.2. So the train site is 0.8. The random state is 0. And what we're training the image paths. Because right now, what we do is transform the images that we have here in an index of raw vectors. Here, you see the numpy function, the image path, and the steering. Right now, all the images from the steering, well, if you see it here, I think that it's easy to understand if we have it here. For example, here are the images of the center camera, and then in the are the images. Basically, I think that here of how an angle of the steering. So there are two types of images. So we have in a NumPy array. So we have to split the data, have samples. So right now I'm just using a sample of the data because we don't have a lot of time to train. So we have training set and validation set. This is the angle from -1 to 1 from the angles. When we define that, you can see it from -1 to 1 here. We define the center of the pins of the angles of the steering from -1 to 1. So uh, then we're going to process the images. So one of the things that we're going to use is first we're going to crop the images to remove unnecessary features. That it's important because it's not all the filters and not all the pixels are good to train. So maybe that process here requires a lot of iteration and understanding of how we can do that. Another step that we talked it's about normalizing. Normalizing is that they have the same mean and the same variation. So the Gaussian, so that's an approach to normalize the data, and all the images have the same pixels and the same filters. That a filter, as you remember here, when we talk about the filter, I think that here it was. All the filters needs to have the same patch, 5 times 5. So a normalization is going to do that in a huge scale. So a normalization we take and we have that patch to the flattened layer, and we have the first output. So that's here the step. We're going to get any image. First, we read the NumPy array with the images, and we process. So basically, I think that I will put it here a little bit bigger. We will compare and processing how the image works. So what I'm doing here, I'm taking the image, the original image, and the pre-processing. What is the pre-processing? Is that function. First, we crop the images, then we change the color, and basically some things of images or maybe paths that are not good in the pixels. That is working basically with a lot of work of experimentation. It's not that kind of easy. So basically here we have the original image that it's here in the processing of the center camera, and we have the pre-processed images. So we have the X training and the X validation in a NumPy array. So we're going to define that, and we're going to work that. So now we're going to work how a random iteration of the main work. So basically we have for train we have the first 42 times 100, and then it's like the train and the set. That's important to understand. So right now, for the main purposes of training, I'm going to load a ResNet 50. That's a pre-trained convolutional neural network to do that. So I think that here we have to I'm downloading the data from the huge ResNet that have some parameters, and then the input shape here. Is important to understand that here the input shape here it's the how the main pixels that can be adapted. What is the input shape here? Here is 32 times 32 in the main images. Here it's 100 times 100. So I'm loading here, and that's a pre-trained model. Maybe that's a huge trick when we don't have like a lot of resources to train. So here we load the ResNet layers in the list from the first elements there. So we're going to do that. The main process that we're going to be doing here is that we have the left camera, the center camera data. We have the random shift and rotation, and that is basically the main transformation that we do with the data. What do we do with the data? Basically, that's that's visualization, that's cleaning. Then we have to validate the data, divide the data, and the image processing. There are four parts: necessary features, the Gaussian blur. It's to select. Here I select the filter 3 times 3, and then we have the processing. So the Gaussian blur is one of the most important thing because it's how you can select the patch to train and how the convolutional filters work throughout the time. So that's we're working here, and then we're going to use an NVIDIA model. They in the paper they train in laboratory this model for this feature. So they put it in Keras. We can define that model. The first layer that we're going to use is the ResNet. Well, basically in TensorFlow there are three components that we have to have like in memory to train. One is model.add. It's like we add dense layer throughout all the activation function, and we define the drawdown. That's how the loss can be measured in the hyperparameters. Then we have to select the activation function. Here in the model.add dense, we have the activation function. The main activation function that we talk about here is that in the neural network we have the X vector. Right now we have the steering and the image vector. So we have to reduce linearity. We have a lot of linearity here in the model. So maybe if you remember, when we use LU, what we're going to do here, we have like if X is that function is X is more than 0, we have X like it's like a linear function, and then we have X to X minus 1. that's because we need to normalize the data, and all the filters and the patches throughout the forward and the back propagation needs to be the same. So that we're going to use to test the model. Maybe in images, we're going to use normally one of the families of ELU. ReLU is good if we don't have like a huge data, we have a small data set. Imagine you want to classify, I think that, no, I think that 200, I think, images. ReLU can be good because it puts 0 and X to the function between negative and positive parts. One of the main tricks in huge neural networks is use ELU and leaky ReLU because we're going to use add to reduce nonlinearity. That's important to understand because that's how basically we're going to do. We need to have a constant function that X we need more than 0. So one of the main options that we have is ReLU or ELU. Or leaky ReLU basically sometimes can be useful, but we have to make another data augmentation process. So then we have the droplet and how the last function. The optimizer, basically, it's how it can be Adam. There are a lot of optimizer and how we can use. Then another common function that we have when we're training Keras is the model.compile. Then we define three things: how we can measure the model. There is a mean square error. The optimizer and the metrics will be accuracy. So we define that, and I will print the model that we're going to train. The first layer will be with ResNet. Then we're going to go through all the parameters. Here you can see we have 2600 mil parameters. So that's like how it can be. The first dense function will be set up as and in the throughput. You see the throughput is 0.5 here. So I'm going to use the next trick common in training neural networks in Keras is model.fit. We have that parameters. Here I'm going to put only 25 because from a lot of time. The byte size is, and we have to define the byte size as how the size will be throughout all the images. That's the process between forward and back propagation. So I will start to train here. Maybe it will use like a minute, I think, because we have a setup like a TPU here. But if you try to do it that locally, I think that will be like 20 hours, I think, because we have a lot of images. Here will be, I think that will be faster because we have a TPU working. So basically here, we have to think about the accuracy. Here, the accuracy in the field of self-driving cars, they are not high. They're like 30% or 40%, because we're going to only adapt the parameters, and that parameters that the neural network learn will be adjusting with the maybe Google Maps API that is working there. So we have like 30%, we have 0.5, 25% of accuracy would be good for that task. Is not, we don't have 1% of accuracy, more than 20% is good here, because it's basically how the problem works. And then we're going to use the validation and training, and we're going to use 25 epoch. What can be the tricky here? If you want to test, you can change the activation function. I will use, example, ReLU in the first and ReLU in the second. It's a good approach to normalize the data. And I will see how it works here. We have lost accuracy and the last value. Here you see the model work better. How I know how to put this, like, you have to start to see the best parameters. If you have ReLU here, what I'm using ReLU is not random. ReLU, we need to be a constant to understand all the work in the functions. So we can try ReLU, ELU, maybe leaky ReLU because X is a constant in values more than 0. That's you have to understand because if, for example, I use a step function 1 will be it can be feeding a convolutional neural network. A sigmoid, we have like that function in mathematics. Basically, it's a separable function. So that's I'm going to try going with ReLU, and then we have to see how it fits here. Here is it's like 40%. It's one of the best accuracy here. And then we start to train, and then basically that's the process of training. How we can base, I think that model punto say it's like here what I'm doing is that's a model punto save is like here is to save the model. That's a format to use it to put it in production, save the model. That's basically a single step. So here you have the notebook here, and then you can try it here. Basically, one of the good approaches here is not just copy paste the code, is basically understand what the code is doing, and basically that. I will show here at the end here some a video here. I think the video of a simulation here of how that model works. Here you have it like the model. It doesn't have some. So basically, with the parameters that we train, just when we see that images, and then basically the autonomous car is like using and the parameters from the steering and the center and the camera, and basically is working autonomous. Here you see the angle that is using here is the main adjustment that we use when we use the data augmentation process. So basically, the deep neural network have to remember basically how it can adapt the steering direction throughout the velocity, so it can be working. So that another feature, good thing that we can do it here is basically that saving model. We can use it here, and we can code it like a game in Unity, or basically put it in production. That model here is not apt like to be put in production because you need to set up like sensor and how it works. So basically, that's all we have. And thank you for being in the workshop. There is a question there. Uh, this wouldn't reformer learning algorithm be good for match for this ML problem? Well, basically, in production, they can use a Markov process in reformer learning when they adapt that to be used like in production. One of the main steps here is we have the convolutional neural network to adapt here to the main stack of image classification. And then when we use like in reformer learning a Markov process, maybe uh, you can use to adapt to the sensors. Yes, there is an approach to put it in production, but to train the model, it's like an image classification task, maybe a convolutional neural network. There are a lot of architecture of CNN, but basically it means image recognition. And another approach that can be used is object detection. YOLO V7, YOLO V6, it's another approach, but the main task is image classification and image training. Yes. Does activation function affect weights? That's a question there. Yes, because I need to show you the screen to explain that, because when you have an activation function, why it well, the main task that you have to understand with activation function is that we have a raw vector x, so the type of activation function would reduce linearity. So if we choose, like, for example, ReLU or ELU, the weights can be learned more in the flattened layer. So basically, it's important to know what activation function, because throughout the process, we have to understand that there may be a brain of one layer and pass from the first layer to the hidden layers, and the activation function, it's important to to. But I think that the weights can be adapted without understand, maybe it depends on the activation function. So maybe for convolutional neural network in practice, that's like, from my experience, we ELU, ReLU, and family, and leaky ReLU are one of the main approaches. But you can start to try with sigmoid. Basically, in artificial intelligence code, we are like experimenting. There is no anything written. It depends on the data, but that's an approach.